Hi everyone, welcome to the next lesson on integration, which is now on integration by substitution. This is a bit of a strange one because this in your books will be page 98 onwards. Now, if you look at page 98, it says standard patterns for integrating expressions. I'm not going to go through that idea for the simple reason that it is actually not that easy to see. I mean, feel free to read the notes and do it the way the book says. However, I'm going to focus on one method that allows you to do section 6.5 but also 6.6. Okay, it will do both in one go. It's one less method to remember and it always works. Whereas the way that the book does it, I think is a little bit convoluted and I think will actually confuse people. So this section, although I'm going to focus on it for looking at types of questions 6.5 first, and I'll do a separate video officially on integration by substitution. This will cover both. Okay, so let's go. This is where we've got questions where you are going to have a part of it, the integral being something that you can differentiate, and within that differential you'll get the other parts. Okay, bit of a weird one to word, but you'll see what I mean now. So, for example, the integral of 2x over x squared plus 1 dx. This is an example 9. If I look at this, there are elements of it that are differentials of the other. For example, if I imagine this x squared plus 1, the bit you can see at the bottom, if I differentiate that, I will get the numerator. That's going to be particularly useful for us because what I can do is I could say, well, let's let some function, some variable u, be equal to x squared plus 1. If I differentiate that, du by dx is equal to 2x. Now, what I'm going to do at this stage, I'm going to consider the differential signal, the symbol for differentiation du by dx, I'm going to consider that as a fraction so that I can actually multiply across and whatnot with it. This means I can get du is equal to 2x dx. And if you look at what we've got there, I've got my 2x plus 1, which is u, but now I've got this du, which is 2x dx. I've got 2x dx up here. So what this means I can do, it means that I can actually rewrite this expression, this integral, but not in terms of x, in terms of u, because at the moment you can't integrate 2x over x plus 1, we don't know how. But if I write it in terms of u, replacing my red bit, 2x dx with du, and replacing my x plus 1, x plus 1 with u, I've got this, du over u. This is the same as saying 1 over u du. Sometimes when the numerator of your integral is 1, they will put the du up there. Okay, so the fact that it's 1 over u or du over u is the same. This is now a standard. 1 over u is natural log of u plus c, but we've already established u is x squared plus 1. So this is the same as natural log x squared plus 1 plus c. And there we have it. That is now fully integrated, but by doing it a slightly different way than the book says. So what we're going to do each time we are going to find a u, we are going to du by dx that. We are then going to rearrange for du or rearrange for the thing that we can substitute in. So another example, this is example B. The integral of, I'm going to have to swap pens. Hopefully this will work in time. Let's go for this one. Okay, let's go for the integral of cos x over 3 plus sine x dx. Again, look at something where you can differentiate one and get the other bit. Now in this case, what I could say is, well, if I set u is equal to 3 plus 2 sine x, that can differentiate du by dx, and I get cos x, meaning that du on its own would be cos x dx, or also 2 cos x dx. So this gives me a logical thing to do my substitution with. I could say u is equal to 3 plus 2 sine x. So I'm going to get a similar sort of thing when I have a u on the bottom, okay, when I put my substitution in. So this is going to be over u, but look at what we've got on the top. I've got cos x dx, but I don't have cos x dx here, I have 2 cos x dx here. So I'm making a slight change. If I go started by 2, a half of du is cos x dx. And notice that now I have listed what my cos x dx is, that's this red bit, so I can now replace it. I can replace cos x dx with a half du. Let's put the half out there because it's a constant. So I've now got half du over u. By the same logic as over here, that's going to be a half of natural log of u plus c, or a half of natural log of what u is actually equal to, which was 3 plus 2 sine x plus c. Okay, so again, all we are doing at each of these stages, we are selecting an element that is something that can be differentiated to give another part of it. We are differentiating it to show this step, and we are substituting in both the symbol u for that element, and then replacing the differential dx with du. An important point when you're doing this, and this is something I must really stress, you are changing everything. You don't pick a variable that differentiates the other but leaves x's in. You've got to be able to cancel out everything. Okay? When you change the variable from x to u, and this becomes a dx to du business, I can't have any x's in there anymore. It has to all be in terms of u. Otherwise you will have problems. Okay, so let's try another one. Again, following the same steps all the time of u, du by dx, then rearranging, substituting, differentiating, integrating them, and then after you've integrated, going back to what you need. Okay, next one on this list is the integral of 3 cos x sine squared of x. Okay. Now, a logical thing to do at this stage, when you're selecting your u, you're going to select the thing that is a function, the thing that's got something going on the outside. In this case, it's sine squared of x. I wouldn't pick cos because I wouldn't generate a squared from there. So I'm going to have u is equal to just sine of x. Okay? So this is now a u squared. That means that du by dx differentiates sine, you get cos x. Okay? So du is equal to cos x dx. Now we've got enough information. That 3, it's a constant, I'm going to put it on the outside, just so I don't need to think about it just yet. So now I've got 3 loads of, I've got my sine squared x. Sine squared of x, well that's u squared. Okay, so I've dealt with that. Cos x dx, that's the same thing as I've got here for du. So I've got 3 loads of the integral of u squared du. Or 3 loads of, integrate this, that's going to be u to the 2 plus 1 is 3, divided by 3 plus c. Or, to freeze cancel, u cubed plus c. Or, u is sine x, so therefore sine cubed of x plus c. Okay, and we've done it by selecting u as sine x, differentiating it, replacing the cos x dx with du. Notice that even though they weren't next to each other, it doesn't matter, they are connected. Okay, they're commutative, so it doesn't matter the order. Okay, part D. You could have x into x squared plus 5 all cubed dx. Again, you can see, same as what we had here, I've got something, some variable that is going through a function. This is a function of a function. We don't need to worry about chain rule here, because we just say, well, okay, you could be the bit on the inside. X squared plus 5. Which therefore means du by dx would be equal to, differentiating all these, 2x plus 0. Or du is equal to 2x dx. So we're in a good nick. However, notice there's no 2 here. We're going to be replacing, when I come onto my substitution space, x squared plus 5, which is u cubed. So I've got u cubed. But then I've got x dx, so I don't have 2x dx, so I need to rearrange. X dx is a half of du. So I'm going to have a half of u cubed du. Okay, very similar to what I had before. When I integrate this, I'm going to have half of u to the 4 over 4 plus c. Multiplying in the fraction, I'm going to have u to the 4 over 8 plus c. And then going back to what u is x squared plus 5. I'm going to have x squared plus 5 all to the 4 over 8 plus c. You do not need to expand the brackets. Okay, and there we have it. So, that's example 9. Example 10 has some more slightly complicated ones. I will go through them as well, and then give you a bit of a chance to do this next bit. So, in example 10, you've got here, part A is the integral of cosec squared of x over 2 plus cot x all cubed dx. Got to be really careful with this one. As a general rule, if you've got a fraction and you're being able to do it by substitution, the fractional bit, the bit on the denominator, that's the bit that you're going to set to be u. So I'd be trying out, and it might take a bit of trial and error, you might not get the right substitution first time around. I'm going to set u is equal to 2 plus cot x. Now, if I differentiate this, you might need to go back to your formula books, okay, because we've done cot x before. I will just show you the page that you'll need. I have it on here somewhere. Okay, so if I go to the differentiation section of the formula book, which is here, we're looking for, well, 2 we know, but cot x, you can see, goes to minus cosec squared of x. That's quite handy because look at what the top is, cosec squared. So 2 differentiates to nothing. Cot differentiates to minus cosec squared of x. In other words, du is equal to minus cosec squared of x dx. This isn't negative though, so I'm going to put the negative over here. So I could have cosec squared dx is now minus du. That means that on the top of this, I'm going to have a minus du, the minus outside. On the bottom, I'm going to have my u, 2 plus cot x.